Welcome back. Today I will discuss separation axiom of topological space. This type of axiom actually very important in topological space. In topological space there are different type of separation axiom: T0 space, T1 space, T2 space, normal space, regular space. This concept actually very important for higher study, also for any competitive exam. So at first I will highly recommend you please see today's video with pay attention. When a topological space is called T0, when a topological space is called T1, T2, this type of concept actually very important. Okay? At first I will say T0 space, then T1, T2, and I will say difference between this space, and in my next video I will discuss what is the normal space and what is the irregular space. Okay? Let's see. First, T0 space. Topological space is T0 space that provided that for each pair of distinct point there is an open set that contain one point but not other. That means if this is the point x and y, then x contain one open set u, but y does not contain any open set. Similarly, this is the space x and this is two different point x, y. If y contain an open set u, then x does not contain any other open set. This is the T0 space. Then next some few higher dimension T1 space. And definition of T1 space is a topological space is T1 space which provided that for each pair of distinct point x and y there exists two open set u and v such that x belongs to u but y does not belongs to u. Otherwise, y belongs to v but y does not belongs to. X does not belongs to v. And the picture would be such type. This is the point x and this is the point y. Then x contain the open set u and y contain the open set v. Notice here x belongs to u but y does not belongs to u. Similarly, y belongs to v but x does not belongs to v. Here these two open set may or may not be distinct. If these two open sets are distinct, then T1 space and T2 space are equal, because when these two open sets are distinct, then this space is called T2 space. This is the difference between T1 space and T2 space. In T1 space, these two open sets u and v may or may not be distinct. A topological space is said to be T2 space that provided that for each pair of distinct point x and y there exists two open set u and v such that x belongs to u and y belongs to v and u intersection v equal to phi. That means in the space x, if we consider two different point x and y, then always there exists two open set u and v which does not intersect. These open sets are different. This is the difference between T1 space and T2 space. In T1 space, these open sets may or may not be different. So that means definition of T2 space is for any two different point xy in x, there exist always two open set such that these intersection of these two open set are disjoint. As for example, now let's see some example. R with in discrete topology. Is it, at first I will say, is it Hausdorff? Is it T2 space? Just think. If we consider two point xy in this space, we all of us know that the only open set in discrete topology is phi and x. If we consider 2 point xy in R in discrete topology, there does not exist disjoint open set. Open set containing x and open set containing y is only capital X. So there does not exist any disjoint open set containing x and y. So R with indiscrete topology, not T2 space. I hope my all viewers have understood this is. Now consider X contain the element A, B, C, D, and the topology denoted this defined by this X, phi X, singleton set A, singleton set B, set containing the element A, B, set containing the element B, C, and set containing the element A, B, C. Is this topology is T2? Sorry. Consider two distinct element AB. This is A and this is B. Then notice the open set, this open set and this open set. This is the set containing the element A, this is the set this open set be the set containing the element B, and these open set are distinct. Next, if we consider AC, then here A and here C. Then these open set containing the element singleton element A and these open set containing the element BC, these two open set, we can consider these two open set which are distinct also. But if we consider AD, notice there exists no open set containing AD. Only there exists one open set which contain AD, this is X itself. But X contain A, B, C, D both. So these two open set, these and if we consider X, then these two open set cannot be distinct. So this is not be T2 space, but this is example of T1 space and also T0 space. I hope my all viewers have understood this is. Okay. Similarly, R with indiscrete topology, this is also example of T1 space, but not T2 space, because the open set are not distinct. So T2 space is for higher. I hope my all viewers have understood the difference. Okay. With discrete topologies, this is always T2 space, and since T2 space, this is obviously T1 space. R with discrete topology always T2 space, and since T2 space, then this is obviously T1 space. Consider X equal to A comma B. Then tau equal to phi set containing the element A, set containing the element B and X. Obviously, see the picture. This is the topological space X, and consider two distinct point AB. Here the open set containing A is this. This is the open set containing A, and open set containing B is B itself. This is B. Consider this is U and this is B. Notice A belongs to U, but B does not belongs to U. Also, B belongs to V, but A does not belongs to V. So, obviously, this is T1 space For this condition, since A belongs to U but A does not belongs to V, B belongs to V and B does not belongs to V. Also, these two open set are disjoint. That means this is example both T1, T2, and since T2, that means this is obviously T1 space also. R with discrete topology always be Hausdorff space. Similarly, our real line with usual topology is Hausdorff space. Actually, metric space always be Hausdorff space. Metric space always to T2 space, because if you consider 2 point AB, here the open set look like ball type and distance between these 2 point, distinct 2 point is R. If you consider this is R over 2, if you consider the open ball, such type, this is U and this is B, and notice, and this radius of this open ball is here R over 2, here also R over 2. Radius of this open ball is R over 2 and U intersection V equal to phi. So, metric space always T2, and since T2, then obviously this is T1. That means every metric space is also Hausdorff space. Also, real line with discrete topology is always Hausdorff space. This is the example of Hausdorff space, which is actually T2 space. Another name of T2 space is Hausdorff space, we all of us know. Next I will see, a few minutes ago I have seen R with discrete topology always T2 space. Now my next question, R with lower limit topology, is it T2 space? Just check it on self. This is very easy type. We all of us know, here the bases look like this type, closed interval A, open interval B, where AB belongs to R. This is always Hausdorff, because if we consider 2 points C and D in the real line, then always where C not equal to D and CD belongs to real line, then always I will get this type of open ball which are distinct. So, R with lower limit topology, this is the example of T2 space. R with upper limit topology, but question, R with cofinite topology, is it T2 space? Always, because here the open ball is look like those U such that U complement is finite or whole X. If we consider 2.1 and 2, then how look like the open ball in cofinite topology? At first think, in cofinite topology the ball, open ball are such type, those ball such that U complement is finite or the whole set X. So if we consider two distinct point 1 and 2, then open ball would be such type, either R minus singleton set 1, because its complement is only 1, or this would be, this can be such type R omitted singleton set 2, 3, 4, R omitted singleton set, the set containing 1, 3, 5, this type of ball with the open ball containing 1. Similarly, if we consider 2, then the open ball such type R minus singleton set 1, 2 belongs to R minus singleton, the set containing the element 1, 3, 5, this type of ball. This is the open ball that means open set in R in cofinite topology. Now is it T2 space? At first consider, I will prove it by contradiction, consider x tau be T2 space and consider A1 and 2 be the distinct element in X. Since 1 and 2 be the distinct element and since I have considered it, this is T2 space, that means there exists two open ball UV belongs to tau such that 1 belongs to U and 2 belongs to V and U intersection V equal to phi. This is the condition of T2 space. Since I have assumed this is x tau be T2 space and since U intersection V equal to phi, then U intersection V, use the complement both side, then this would be U complement union V complement and this would be X. And since this is the cofinite topology, so this is finite, U complement would be finite and V complement would be finite. Finite union of two finite set is always finite. And since X is R, that means X is infinite. So this is infinite. This is not possible. So R with cofinite topology is not T2 space. I hope my all viewers have understood this is clearly. Okay? Oh yeah. Similarly, when X is infinite set with cofinite topology is not T2 space, does not imply T2 space. But when X is finite set always cofinite topology. This is that imply this is always T2 space, because when the set is finite, then finite set with cofinite topology, this is coincide with discrete topology. As for example, consider x equal to AB and consider x with cofinite topology. Then x with cofinite topology, tau cofinite equal to set containing phi, x means AB, set containing the element A and set containing the element B. And few minutes ago I have seen discrete topology always imply T2. Since when x is finite, then cofinite topology always coincide with discrete topology. So when x is finite, then this is always T2. But when x is not finite, then this is not implied T2 space. I hope my all viewers have understood this is clearly. Okay, well. That means from this concept, T2 imply T1 and T1 imply T0. But converts not always to T1. This is does not imply this is T2. I hope my all viewers have understood till now. Now, consider x be an infinite set and tau be a cofinite topology. Now we have to show x tau is T1 space. For this, let x not equal to y. Then there exists two open set x belongs to x minus singleton set y and but y does not belongs to x minus singleton set y. Also y belongs to x minus singleton set y but x does not belongs to x minus singleton set x. Then x tau is a T1 space, but since x is infinite set in cofinite topology, this is not be T2 space. We all of us know, few minutes ago I have seen. Okay? Today I will stop here. In my next video, I will discuss normal space, regular space, and some concept of some theorem based on T2 space and T1 space. But I will highly recommend you please see today's video with pay attention. And if you have any queries, then do comments in comments box. Okay? See you soon. Stay safe and stay positive always. And don't forget to subscribe my channel for more videos. Thank you so much.